Now we have the pleasure to present for yourselves Professor Maurício Richartz from University of ABC, almost local, you know, it's close by in a different town, but it's close. And he'll be talking about some cool stuff related to superradiance, and I think it was Peter Barker, he mentioned something about black hole bombs, right?
Yeah.
So probably Mauricio is going to talk about related stuff, or even black hole bombs, I don't know, let's see. And please, Mauricio, whenever you're ready.
Thank
Thanks.
you. Um, Thank you, Gabriel. So first of all, I'd like to thank the organizers, especially Gabriel and Giorgio, for inviting me and organizing all this, the conference and everything else. So the title of my talk is Analog Gravity Experiments with Fluids, and the subtitle is Superradiance and Ergoregion Instabilities in Vortices. And in fact, in the end, there's an ongoing project which we try to actually observe a black hole bomb in the lab, and maybe if there's time in the end, I'm gonna give you some details about this, but this is an ongoing project yet. So let me get started. So the idea is that behind all this like analog models of gravity is that we try to set up in the laboratory the conditions to observe some of the phenomena that we predict to happen in the universe, but that we can't actually observe. So some process in the universe, especially when gravity and quantum physics are both important, are extremely hard or impossible to observe. We've seen some talks this week about experiments that try to investigate the quantum properties of gravity and the quantum nature of gravity, but this is in some sense different types of experiments. And the idea is that can we observe Hawking radiation or cosmic inflation or other phenomena of the universe using analog classical or quantum simulators. And this goes back to Bill Unruh's seminal work, and where he basically set up this framework to do this. So analog models of gravity are systems that can mimic curved spacetimes, curved spacetime effects, both classical and quantum. For instance, Hawking radiation, superradiance, and they lead naturally to the question: can we observe, for instance, Hawking radiation, the Hawking effect in a laboratory? And this was actually Unruh's, the title of Unruh's seminal paper. And the abstract is, it is shown that the same arguments which lead to black hole evaporation also predict that a thermal spectrum of sound waves should be given out from the sonic horizon and transonic fluid flow. And just to explain how, I mean, the reach and the capabilities of such analogs, and how I see them, how I understand them, I've put this slide in here, and this is to show you the first, as I call the first success of the theory of the idea of using these analog systems, and this was the idea of Ted Jacobson in I think 1991, and then this basically was the first time, like the first paper that really brought the attention to this subject, so that people became more interested in this. Bill Unruh's original paper is from 1981, This was 10 years later, and if you see the citations of Unruh's original paper here, I think the first 10 or 15 years, there's like less than 10 citations. And then around this time, after this work, and then other people also worked on this idea, really people became more interested, and you can see that it's the number of citations. I mean, it's growing. It's still growing nowadays. So the idea, Jacobson's idea, was to use these analogs to try to understand better and try to solve the so-called Transplanckian problem of Hawking radiation. So I guess the abstract explains it better than I could if I tried myself. So the role played by ultra-high frequencies or ultra-short distances in the usual derivations of the Hawking effect is discussed and criticized. The question, would a black hole radiate if there were a Planck scale cutoff in the rest frame of the hole, is posed. Guidance is sought from Unruh's fluid flow analog of black hole radiation by taking into account the atomic nature of the fluid. Two arguments for black hole radiation are given which assume a Planck length cutoff, and then it goes on, and neither argument is conclusive, but they do strongly suggest that in spite of reasonable doubt about the usual derivations of black hole radiation, a safe derivation which avoids our ignorance of ultra-short distance physics can likely be formulated. So the way I see these analogs is that you can get ideas from them and use these ideas in actual gravity, even though like this are condensed matter systems, fluids, and so on. And you can also try to do the other way around. You can get ideas from gravity and try to apply them in these analog systems and try to see these effects that you predicted for in gravitational systems. For instance, Hawking radiation. Like almost 30 years after Unruh's paper, the people started setting this up in these analogs in the laboratory. Here are the first few examples that I know of. So you can use surface waves propagating on water. You can use light pulses propagating in optical fibers and set up an analog event horizon in this case. You can also use Bose-Einstein condensates and investigate the propagation of density perturbations. And there are many other systems that people use nowadays, fluids of light and other things. In this talk, I'm going to focus on some experiments I've been involved with. So this is the experiments that have been that take place at the University of Nottingham by the group led by Silke Weinfartner, and I've been involved with some of these experiments. This first picture here on top is an analog black hole using water, and this is a draining flow, and you see here the perturbations on top of the surface of the flow. And this led to some experimental research, some experimental results, which I'm gonna talk about today. So the observation of rotational superradiance in this system, and the observation of the characteristic oscillations, which are analogous to the quasi-normal mode oscillations of a black hole in this system as well. I've mostly involved in the theory analysis, theoretical analysis, but I've been there quite a few times. I've helped with the experiments, and I'm gonna try to explain what we've seen and how we did that. There's also some more recent, a more recent experiment, which is basically shown in this picture here. This is from this work, which I wasn't part of, but it's a very recent one from earlier this year. And it's, in some sense, the same idea to observe the propagation of surface waves on a fluid, but this is using a superfluid flow, so it's superfluid helium. Its temperature is around 2 Kelvin, 1.9 I think, and there are several advantages compared to the normal fluid flow situation. Especially, you can drastically reduce the effects of viscosity in the superfluid case, and this makes it in a way the analogy of this system with gravity better. And in the end, I'm gonna talk about this work in progress, which is an attempt to observe a black hole bomb in this system. So superradiant instabilities that grow in time. All right, so before I started the experiments, let me just go quickly through the basic theory that we need to understand these systems. We basically have a fluid on a basin, and we want to investigate the perturbations on top of it. And but to do that, first we need to understand the background flow before perturbing it. So in the case of this, when we want to investigate surface waves, we need an interface between the fluid and another fluid. In this case, it's just air, or it could be another fluid, but I mean another liquid. But here's air. The interface water-air, and the background equations are just the hydrodynamic equations of a inviscid and irrotational fluid flow. So here we assume axisymmetry and a constant density fluid, and basically have the continuity equation here, the Euler's equation, and the condition for a irrotational flow. And we want to determine the height, the depth of the fluid in this basin, and this is in principle the boundary of the system. So this, in the end, is a free boundary problem that we want to determine the height when we subject this system to boundary conditions. And the simplest solution when the depth is constant is just the so-called draining bathtub flow, where you have that both a radial and an angular velocity are diverging with as r goes to 0, so it's 1/r behavior. Of course, this can't hold for like when you go to very small radii, but it's a good approximation if you're far away from the vortex center. And here's the picture of the real experiment. We can measure this, and it's a good approximation away from the center or the drain. I'm going to talk a little more about the experiment later, but the idea of this, the analogy, is that you have perturbations propagating on top of this flow, and the velocity of the flow is getting larger and larger as you go towards the sink, and at some point they will get so large that there will be the flow will be faster than the propagation that are trying to escape from inside the vortex. So as I'll show in the next slide, this can be done. This analogy can be made precise, more precise in terms of an effective metric. And in the end, you find that there's an analog event horizon exactly where the velocity of the perturbation, which is denoted here by C, is equal to the radial flow velocity. Of course, you don't need the angular part here. You can set this to 0, and then you just have a purely radially draining flow. But since I'm interested in other effects that are associated with rotation, I've included this in here. And you can also have the analog of an ergoregion here. So if the total velocity, so the square of this one plus this one, is equal to the square of the propagation speed, then you get the analog of an ergoregion. And then you can study perturbations on top of the system by perturbing the background equations, so the continuity and and Euler's equations. In the end, the most general case, you find that if you have surface waves with frequency omega and wave number k, they will satisfy a nonlinear dispersion relation, which is given by this expression here. This is just the frequency in the comoving frame, and then you get this tan H here, which is typical of this the water system, and this term here is depends on the surface density of the surface tension of the fluid. And I mean this dispersion relation has been known for like more than a century, but the thing is that when you go to long wavelengths, so when kh is much smaller than 1, this becomes a linear dispersion relation, and you can identify the wave speed to be just the square root of g times h. H is the depth of the flow, g is just the acceleration of gravity, and in this case, when you have this long wavelengths, then you can match the theory with for this waves with the theory of a scalar field propagating on a curved space-time. And in fact, you don't even need to go to this to the frequency space. You can work directly with the wave equation, the perturbations of the Euler's equation and the continuity equation, and you can show that they will satisfy in this regime of long wavelengths this equation here, which you can here, so delta H is just the perturbation of the height, and you can map this to the Klein-Gordon equation of a massless field in a curved background defined by this metric G mu nu. And it will depend on V, basically, and C, which is the square root of GH. Doesn't really matter, I mean, the specific details here, but the important thing is that this metric exhibits an event horizon exactly where the propagation speed equals the radial flow speed. And this is what we try to explore in the experiments. It's important to note that there are some key assumptions, as I mentioned, that make this analogy work. So first of all, you need to be in the linear dispersion regime, so long wavelengths. Secondly, I mentioned, but maybe I wasn't highlighted, that you need to be, the flow needs to be irrotational. Otherwise, you have more degrees of freedom that can couple to this scalar field, which is basically representing the perturbations of the surface of the height. And you also need the Euler's equation. So you can't have viscosity here, otherwise the analogy also breaks down. But some of these things are hard to eliminate in a real experiment. For instance, as I was explaining earlier, if you go to small radii, this velocity, the velocity won't look like this anymore. We'll probably get some rotational core, or like it's some deviation from this, and this will make your analogy break down. Also, there's always some sort of dissipation in the system, so viscosity is always there. So you can try to work in regimes where it's less important, but in some sense it will always be there. And the same with dispersion. I mean, you always have surface tension, and you really need to go to long wavelengths to have the to make the analogy work. And as we will see in the experiments we do, we can't really neglect all these things. For instance, it's hard to work with our setup in the long wavelength regime, and it's also the rotational the rotationality assumption is a good one if you're far away from the vortex, but not close to the center. And as I'll show, we also have this dissipation at least in the water system. In the superfluid, it's I think 2 orders of magnitude. The viscosity effects are at least 2 orders of magnitude smaller, so it's easier to make this work. So let me start with the first experiment, which is the attempt to observe superradiance scattering in these water vortices. And this has been studied theoretically more than 20 years ago for analog black holes, and even like in the 70s for real black holes. I think there was a talk on Wednesday where it was mentioned Zeldovich's cylinder, which was basically the precursor of the black hole superradiance, and also Penrose's effects, which were the precursors of the wave amplification by superradiance in black holes. And here are some theoretical numerical results that try to understand this amplification in analog black holes. So this is the work by Berti, Cardoso, and Lemos in 2004, where they basically used the Klein-Gordon equation in this effective space-time and numerically calculated how much the amplitude of a wave, an incoming wave towards this rotating black hole would be amplified. And as you can see here, if this is the frequency, and here's the reflection coefficient, so basically the amplitude of the reflected wave divided by the amplitude of the ingoing wave. And you can see that if the frequency is negative, so counter-rotating waves are always absorbed, so the reflection coefficient is always smaller than 1. But co-rotating waves, if their frequencies are sufficiently small, so in this region here, they can have reflection coefficients greater than 1. And here's just a close-up picture of this region here, where you can see the part where the reflection coefficient is greater than 1. The threshold where the reflection coefficient goes back to 1 is just given by the usual superradiance condition, which is the frequency is the azimuthal number m times the angular velocity of the scatterer, here the analog black hole. Here the results are for azimuthal number m equal 1, but similar results are found for other azimuthal numbers. Me, Silke, and other collaborators, we have also worked on this, and we try to consider a more realistic model, thinking that we would be able to try to simulate, to observe this in the laboratory. And I think I don't have time to go into the details, but basically we did the same kind of calculation. We model we try to solve the background equations together with the perturbation equations of for surface waves, and instead of using we parameterize our system by two quantities, just the angular velocity at the event horizon of the analog event horizon, and the analog surface gravity. And for different configurations, we basically also see this amplification, so the reflection coefficient greater than 1 if the frequency of the wave is sufficiently low. And then we try to see this in an experiment. So here's a sketch of the system. There's a this is the water tank. There is a drain hole in the middle, 4 centimeter diameter, the diameter of 4 centimeters. There's a wave generator in one side. There's a water inlet on the other side, and this creates a draining bathtub flow here. And so the water tank is basically 1.5 by 3 meter. It's a closed circuit, so water is pumped from a tank that is sitting on the bottom of this tank here, and so water goes down the drain, and then it comes back through the wave inlet, pumped by with the help of a pump, and then we wait sufficiently enough until we get a stationary flow. And there are some cameras and light sources which are placed above the tank. Here's the actual picture of the system. Here's the wave generator. This is an old version. Now there's a more a better and more precise wave generator, but this was the original one, just a spinning wheel that drives this large metal bar up and down the water. Here's the drain hole. Water is green because we need some sort of dye to observe, to capture the surface of the water by with the camera, and to help analyze the data. Here's the data from the experiment after some filtering has been performed, which I'm going to explain in a bit in the next slide. But basically, we create a plane wave using the wave generator that propagates and scatters off the vortex. The frequency range we use is basically from 3 to 4 hertz, and the fluid in the experiments was around 6 centimeter deep. And this is, you see here the pattern of the incident wave plus the scattered wave, and you see the interference pattern in here. So basically, the data we acquire gives us the surface of the flow as a function of time for each position in the tank, for each coordinate of the surface, a spatial coordinate. And then we Fourier transform the signal in time and filter out the excitation frequency, which we know by looking at the data, or we've already calibrated our system, so we know our wave generator, so we know what frequency we are producing with a certain settings in the wave generator. We also see some nonlinearities in the system, which show up as twice the frequency of the region of the generated wave frequency, but they are, I think, in our experiments, they were less than around 5 or 10%, if I recall. And we also need to filter out the background flow, which is basically zero frequency. So we just see the waves in the data. And after we filter out these frequencies, we were only left with the actual wave that is produced and scattered, and we then decompose it into the different azimuthal numbers. So just we also do these integrals numerically with the data to make the decomposition, and we end up with a sum of an incident wave plus an outgoing wave with different k vectors, k numbers, and we want to basically compare them and see if we can find some amplification or not in these amplitudes. So here, just for different frequencies, the different data we get. So here's just the tank X and Y in meters. Here's one set of data that we get after we do that Fourier transforms and decompose into azimuthal numbers. Here's in real space, so coordinate space. So here x, basically, sorry, the distance r from the center of the vortex, and here's the amplitude. So the dots are the data, the experimental data, and the lines are just fits to cosines and sines. And here's the Fourier transform of the data, and you can see here. So here's the k space, so wave number in the horizontal axis, and you can see. So basically, this is negative m modes. These are the positive m modes. Negative k is basically the ingoing wave. Positive k represents the outgoing wave, and you can tell here that the m equals 0 and m equals and the counter-rotating modes are basically being absorbed by the system. So their amplitudes are getting lower. So the amplitude of the reflected wave, the scattered wave, is lower than the amplitude of the ingoing wave. On the other hand, for the positive M modes, we see the opposite. So we see that the scattered wave has an amplitude that has grown in comparison to the incident wave. And this is our observation of superradiance. We can actually calculate basically the integral of this Fourier transforms here and divide the integrals one by the other and calculate a reflection coefficient, and that's what you see here for the different frequencies and different M modes. And here's the reflection coefficient equals 1 is this line here. You can see that some of the modes. Some of the frequencies have reflection amplitudes, reflection coefficients which are greater than 1. And I think if I recall, the largest amplification we were able to observe was 14%, so reflection coefficient 1.14 plus or minus the error. But there's a detail here which is the following. So this purple line here is the situation when there is no drain. So we basically just closed the vortex and there was no water draining anymore. So just stationary, static water on the system, static flow. And in this case, if you try to calculate the reflection coefficient, you see that as the frequency increases, the reflection coefficient, which was 1 for like low frequencies, starts to go down to, I think it was like 0.8 or 0.7. And this is basically because of dissipation effects, viscosity in the system. So the low frequency waves are basically undamped when they are scattered when they go through the water flow. And if you go here, then you start seeing some dissipation effects. And so if you take this into account, then this reflection coefficient here greater than 1 is actually even more significant, because it's even though there's dissipation, you still get this reflection coefficient greater than 1. So and this sort of dissipation is in the water system is harder to get rid of, but in the superfluid cases, this is more naturally absent. So this was the first experiment. Let me go now to the second one. How much time do I have? Sorry?
4 minutes.
4. There was. So
Let's see if you can amplify those 4 minutes.
Yeah. I'll go very quickly through this one, because this is not related to superradiance nor the ergoregion instability. So it's so this is the second experiment. It's basically the same system, and we try to observe the characteristic oscillations of the vortex, like the quasi-normal ringing that you have in a bell. So we try to identify frequency peaks, peaks in the frequency spectrum of our system, like those in this paper, where they analyzed the quasi-normal ringing of a bell. And there are many theoretical and numerical analysis, and basically here we take into account in our predictions the nonlinear dispersion of the system. So basically the tonnage is in our calculations. And let me skip this one. It's just the theoretical calculation. Here's just, I'm just going through the data, the setup. It's basically the same as before, but instead of producing a wave and throwing the wave towards the vortex, we're just let the vortex sit there and relax by itself. So just the noise of the system is driving this the perturbations. The perturbations are just the noise in the system. We're not producing any wave, not generating any waves on top of it. The data analysis is similar as before. We do a Fourier transform in frequency, and we separate into azimuthal M modes. And then what we find is things like that. So these different colors are different azimuthal M modes. So due to the size of our system and how large the rotation speed is compared to the draining speed, we can't really observe co-rotating modes, but we can observe the counter-rotating ones here. And we basically identify these peaks and we compare them with predictions of the real part of the quasi-normal mode oscillations of a analog black hole. And here is the data, the real data compared to our numerics. The green dots are the data, and black and orange lines are two different numerical calculations, and they agree with the numerical data very well. So this is we were only able to observe the real part of the frequency because our system is we can't observe the decay times of the quasi-normal mode oscillations because our system in the end is not an open system, it's closed. We have like a closed boundary, and we also have this dissipation effects due to viscosity. So we can't really observe the time decay of the modes, but we can the real part is more insensitive to this boundary condition and to the dissipative nature of the system. So we can observe them and compare with the predictions. And so it says here is to have 3 minutes, so let me I just there are 2 or 3 slides here just to give you the idea of the new experiments that are going on in Nottingham. So the experimental setup is much smaller than the big water tank. So this is basically a fridge which is cooled down to 2 Kelvin, and there's a rotating disk here that is creating a draining bathtub flow of superfluid helium-4 here. Here's the drawing, the sketch of the system, and here's the real system. You can barely see here, but there's the water, the surface of the superfluid helium is making a funnel shape here, and it's going down through the bottom. And this bottom here is just this, this bottom here. If the rotation speed, if the flow is not sufficiently fast, then you don't get this open funnel shape, you just get a small dip here. But in any case, this is what has been discussed and observed and presented in that paper I commented in the beginning that has been published this year, which I'm not part of. But now we want to do observe and explore the possibility of superradiant instabilities in this system. This is, I think, if I recall correctly, like 15 or 20 centimeter wide in diameter, and some preliminary results indicate that there are some instabilities in the system, and if the rotation speed is sufficiently fast. Here you see like a very smooth flow in both cases, but as you increase the flow, you see a big sloshing going on there. And we are trying to understand what's the origin of such sloshing. Is it an instability? Is it related to superradiance? Is it related to ergoregion instabilities? Is it something else? natural, something that is well understood in fluids, or what is it? Is it something related to the fact that you have a rotational core in here? So one of the things we are trying to do, at least understand theoretically, is what's the role of vorticity in this system. So the problem, the difficulty is that you get extra degrees of freedom. So instead of a scalar field, you need an extra field here to describe the system. So besides these acoustic perturbations, or like the scalar field that is analogous to a scalar field in a curved space-time, you need an extra vorticity degree of freedom. And the equations are more complicated. You have a coupled system of differential equations that you need to solve. And but that's where we are now. We're trying to understand if this is some sort of black hole bomb instability, where you're basically trapping your superradiant amplified modes in a box, or if it's some sort of ergoregion instability where you don't have an event horizon, so you're basically amplifying this negative energy states that can live inside your system, or if it's something hybrid, which we're trying to understand now. When you have vorticity, you can basically, if the oscillation frequency of this black hole bomb modes and this ergoregion instability modes are very close to each other, basically you can have some sort of resonance between these two instabilities, and then you get something else. So this is an ongoing research. So I hope in the future we'll be able to see this in the lab and tell if you have one or the other, or a mixture of them, or something else. And I'll end here. I just leave some final remarks for you. Thank you.
Thanks, Maurício. Questions?
So thank you very much for the talk. The physics is very interesting. Can you explain better your system is analog to what? Because your system is two-dimensional, no? So it's a 2 + 1 dimensional system. So yeah, we're speaking about 2 + 1 dimensional gravity. So you have a BTZ black hole, is it that? But then in that case, you will need like a negative cosmological constant. First part. The second part of my question is that you are looking at waves, but in 2 + 1, we don't have gravitational waves. So is that matter? But if it is matter, you're using the surface of water for both space-time and matter? So I'm really confused.
Okay, so there's an important detail. The important thing is that we don't have any analogy with Einstein's equations itself. So we're just, the analogy is between the propagation of a scalar field on a curved space-time with the propagation of waves on top of a water system. And in principle, you can do this in 1 + 1 dimensions, or 2 + 1, or 3 + 1. Most of the systems, as I've highlighted here so far, the experiments so far, most of them are 1 + 1 dimensional. So you're just mapping the propagation of your perturbations on this condensed matter system to the propagation of a scalar field on a effective space-time. So what effective space-time is this? So it depends on the system, but basically it depends on the properties of your system. And it's not a Schwarzschild black hole, or a Kerr black hole, or a BTZ black hole. It's just a metric that describes the propagation of your system. And this metric depending on the system, can exhibit an event horizon, the analog of an event horizon in 2+1 dimensions or 1+1 dimension.
Okay, but then so this is fluid dynamics. So why, for example, you have space-time in the title of the papers and these kind of things, they are a little bit misleading. Because if I come to a paper, I think that you're making a kind of analogical computer or simulator where the outcome of your simulation or like your experiments are like the outcome of simulation in lattice simulation that I can take and I can think they really represent the object that you're speaking about. It will be better just to call them like a very interesting system in fluid dynamics.
I mean,
because from outside one perceives this.
Yeah, I think this is one of the main criticisms of the field is that it's you just have the analogy of the propagating fields and not of the space-time itself. But in the end, this propagation fields, these perturbations are seen as effective space-time. So in this sense, is what people. I mean, it's what.
Is it Lorentzian? I mean, I don't understand what you mean by effective. I mean, it's a metric. Everything that has a continuous geometry has a metric.
Yeah.
So I don't understand the analogy and why you can say it in this way. I mean, it's fluid dynamics is very interesting. Let's just call it fluid dynamics. Yes, but for a 3-dimensional, 2+1 dimensional black hole, or for what? They don't specify. I mean, I'm just like confused. I mean, they reproduce a phenomena that is derived and has some mathematical properties similar to Hawking radiation, but it's not the Hawking radiation in general relativity. Gravitational waves in general relativity are related to the Weil tensor and structure that you cannot even imagine and write down in 3 dimensions. So, well, we can talk about this.
Yeah, but it's not the Hawking radiation of a real black hole, but it's the Hawking effect. That's what some people are careful to distinguish them, and they say it's not Hawking radiation, it's the Hawking effect. And it's, I mean, I agree, it's a valid criticism, and many people have that. And
guys, due to time constraints, let's thank Maurício again, and then you can ask him questions afterwards. Thanks.
Thank you.